So this section is all about a topic called optimization. Now these are a lot like related rates problems, except I don't think they're anywhere near as horribly painful. Because we're not having to think of this as like multiple functions swimming around and blah 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 blah. The word problems here are a bit more standard. However, it's going to follow like a similar, like a really simple scheme. So for one, we're going to find an equation for constraints. Then we're going to find the equation to optimize. Optimize. 3, we're going to plug, I spelt that wrong, plug 1 into 2, and then 4, we're going to optimize step 3. However, there is often a secret step 0, which is just to draw the situation to kind of help us understand what is going on here. So these problems actually end up being relatively standard, and there's one that is incredibly common that a lot of people call the fence problem. So what that looks like is something like a gardener has 30 feet of fence to use to enclose a garden beside his house. What is the maximum area for the garden? Right? If I only have 30 feet, I don't want to enclose a garden uh, beside the house. What is the maximum area for the garden? And I forgot to somewhere this needs to be a rectangle, right? The problem is supposed to say that it is a rectangular garden, or they want to make a rectangular garden. Right, we also suppose that piece, right? So step 0 would say that I want to like draw the situation, right? So this is the house. Well, then I need to make a garden using my fence. Well, I want to maximize the area, so how do I find the area? Well, I need to know the length and the width of this, right? So if I call this W, then maybe this is the width or even the height if I just want to call it that, right? If my rectangle's looking like this, then the height, I guess. Um, so I want to maximize W times H. That is my area. Well, I need to come up with an equation for my constraints. Well, if I have 30 feet of fence, then that actually is going to relate to the perimeter of the thing that I need to build. So how many feet of fence do I need to construct what I've drawn? Well, I need obviously to have the width, but how many rows of the height do I have? Well, I have like 2, right? I have to be the left side and the right side has to be h. So I have w plus 2h has to be 30. So I have this constraint equation. I have the equation that I want to maximize. So I'm going to substitute, right? If w plus 2h is equal to 30, right? Well, okay, let's slow down. What's stopping me from maximizing this function already? Well, this is 2 variables going on here, right? If I'm trying to take some derivative and I want to do some optimization problems with it, I'm not really able to do that if I have a function with 2 variables, right? That's not something that we're familiar with doing. So to find critical points, I want this in a single variable. So is there any way that I can use what I have already aka my constraints, to get this area function in a single variable? And I say yes. So looking at my w plus 2h equals 30, if I solve this for w, to say w is equal to 30 minus 2h, then I can substitute that into my area formula and replace w with 30 minus 2h. So now the area is 30 minus 2h times h. And now this is in terms of a single variable, and in fact I can distribute the h to both parts to get 30h minus 2h squared. Well, now the derivative of area with respect to h, derivative of 30h is 30, derivative of 2h squared is 4h. So the derivative is 30 minus 4h, and if I find critical points, I want to set that equal to 0. So can I solve 30 minus 4h equals 0? Well, yeah, that's 30 is equal to 4h, which is just divide both sides by 4, 30 over 4, and that is 7.5. So I figured out that the maximum area has to happen, or at least I have a critical value, when the height is 7.5. Well, if this is my area function, does that critical value correspond to what I want it to? Well, sure, that is a downwards facing parabola, right? It's going to look like this. So any critical value I have, that's going to be the one at the top, which is going to be the maximum value for the area. So yeah, that is absolutely the value that I am trying to find. So I have the maximum area when my height, when this h here is 7.5. So can I figure out what w is? Well, yeah, w plus 2 times h is equal to 30. So w plus 2 times 7.5 is equal to 30. Well, 2 times 7.5 is 15. So w plus 15 is 30, tells me that w itself is equal to 15. So what is my area? What is that maximum area? Well, that's 15 times 7.5. This is not a great number, but hey, that is the number, right? If nothing else, I can just say, 17.5 times 15, and that is an answer that, heck, I'd give you full credit for. But 15 times 7.5 at the decimal is 112.5 square feet is the max area. Now, again, I didn't really like go back to this list and say, okay, I need to do 0, I need to do 1, I need to do 2, I need to do 3, I need to do 4. Right? My intuition for how to solve these problems kind of guided me along the way. So I had a word problem that was describing some visual thing happening. So I drew it to help me understand what the shape needs to look like. Well, then once I draw it, that gives me an idea of what equation to make for the area that I want to maximize, right? I think, what are these two pieces telling me? If you have 30 feet of fence, well, then that's telling you the sides of the shape, which is perimeter, right? So if I have these sides, they need to add up to 30. If I want the maximum area, well, then I certainly need to find some equation for the area. So now once I have this equation and this equation, since I want to maximize this one, I solve or I use my constraint equation to write something for w to substitute that in to get it only in terms of h, and then I maximize that from there, right? Now, but again, this is a new topic in theory to you, right? So having this step-by-step process, draw the situation, find an equation for constraints, find an equation to optimize, and then use one to get to into a single variable, and then optimize it. It's the general approach to these kind of things that hopefully we can learn. So there's another problem that is like on the homework a lot, which is something like uh, find the max area of an isosceles triangle if the two sides of the same length have length A. So this is going to be a little bit of a deceptive problem, which is why I'm working this out right here, right? So if I have an isosceles triangle, that means this side and this side have the same length, so these are both side A. However, I want to maximize the area of the triangle, which is one half the base times the height. Well, the base is whatever this length is, and the height of my triangle is whatever this height is. So how can I figure out the maximum area? Well, it turns out the simplest way to do this is to label, right? I want to figure out a way of writing h. So h, if I look at this right triangle here, I'm able to use the Pythagorean theorem with this half of the base. So this tells me that using the Pythagorean theorem, a squared is equal to h squared plus x squared, where x is this half of the base. So, because I want to get rid of h and just write things in terms of a and the base, then I'm going to write this as h squared is equal to x squared minus, or sorry, a squared minus x squared. So h is the square root of a squared minus x squared. Technically we want plus or minus, but these are sides of a triangle. I don't want a negative side length of a triangle here. So h is just the positive square root of a squared minus x. Which means my area really gets to be written as 1/2 the base times the square root of a squared minus x squared, right? Well, hey, hold on. B, the base of my triangle, if x is half of that, then the base is really just 2x. So in reality, right, the base is 2 x's, so I can write this as 1/2 times 2x times the square root of a squared minus x squared. Well, 1/2 times 2 cancels out, so really my area function is just x times a squared minus x squared. Well, hold on. This feels wrong, right? So this is my area, and this feels like I need to do more, right? Because I still have two variables. I have a and x. But hold on a second. Think of what our variables are in this scenario. X is what I change to figure out what the solution needs to be. However, A is not changing in this problem. It told us the length is A. A is a variable in the sense that I don't know exactly what it is, but it's not like an unknown. It is not something that is changing in this problem. It is something with an actual value that we just don't know. So it is not that this is a function of two variables in the sense that they're both changing. This is a function where x is changing, but a is some constant. A is some number that we're supposed to pretend that we know the value of. So is this function ready to have its derivative taken? Yes, yes it is. Right? This is the area in terms of a single variable, x. So I can take the derivative of area, and I would use the product rule, right? Because this is x times some other piece, right? The square root piece. Derivative of x is 1, so then I just write the second piece out by itself. And then plus x times the derivative of this piece. Well, we're going to have to use a chain rule, right? This is the square root of a squared minus x squared. which we can rewrite as a squared minus x squared to the 1/2 power. Well, the chain rule says take the derivative of the outside piece. So this is 1/2, and then subtract 1 from the power. 1/2 minus 1 is negative 1/2. Leave the inside alone, and then multiply by the derivative of the inside. However, again, a is a constant, so a squared is a constant. So this derivative with respect to x, a squared goes to 0. So the derivative of the inside is just negative 2x, right? We're pretending we know what a is. If a was 2 or 4 or whatever, right, we take that derivative, it's going to 0. So now I have 1/2 the negative, sorry, 1/2 times a squared minus x squared to the negative 1/2 power times negative 2x. Well, I can rewrite this. First of all, this 2 here gets multiplied by this 1/2 and cancels. Also, the negative exponent means I can write this in the bottom. So a squared minus x squared to the 1/2 power means a square root. And then I'm multiplying by negative x on top. So, altogether, the derivative of the denominator is this piece. So my area is the derivative of x was 1 times the inside piece, or sorry, the other piece, so the square root of a squared minus x squared, plus the first term left alone, so just x times the derivative of the second term, which we figured out is this whole piece. So the square root of a squared minus x squared minus, right, x times x is x squared over the square root of a squared minus x squared. So if we want to find critical values, we want to figure out where this is equal to 0. Well, right now we're intimidated, but it turns out this does simplify really nicely, right? If 0 is equal to a squared minus x squared minus x squared over the square root of a squared minus x squared, then because this is negative here, I don't want this to be equal to 0, I can move this to the other side so that this is x squared over the square root of a squared minus x squared is equal to the square root of a squared minus x squared. Well, to get rid of this denominator, I want to multiply both sides by that denominator, by a squared, the square root of a squared minus x squared. Well, that means I'm going to multiply the right-hand side by a squared minus x squared as well. Well, a square root times the same thing in the square root will cancel that square root out. And again, we multiply by the denominator, so we lose that denominator. So I have x squared equals a squared minus x squared. Well, hey, add the x squared to both sides to get 2x squared is equal to a squared. Divide both sides by 2. X squared is equal to a squared over 2. And then take the square root of both sides. Really, plus or minus, but again, we're talking about lengths of a triangle. Side lengths of the triangle, right? So this is only going to be positive. So now I have the square root of a squared over 2. Well, hey, the square root of a fraction goes to top and bottom. So this is a over the square root of 2, which if we rewrite this, if we rationalize this denominator, this turns into root 2a over 2. So I figured out what x needs to be for this to work. So what does the base needs to be? Well, this is, right, x is just half of the base. So really the base needs to be 2x, which is 2 times root 2a over 2. Well, 2 multiply by 2 divide by 2, that cancels, and that's just root 2 times a. So my base needs to be the square root of 2 times a long in order to maximize the area. Well, can we figure out what that area actually is? Only leaving it in terms of a, right? We said this is 1/2 the base, which is root 2a, times the height, which we said is a square root of a squared minus x squared. Well, that's root 2 a squared. So 1/2 times root 2a times the square root of a squared minus 2a squared. Well, a squared minus 2a squared. Did I do this right? Am I crazy? Hold on. Hold on. I did not do this right. I did not do this right. We want x right here, not 2x, right? So we really do want root 2a over 2. So this is, right, I can rewrite this just to make this a little bit easier to write. Root 2a times 1/2 I can write as root 2a over 2 times this big square root piece, a squared minus, and now when I square this, this is going to be root 2 squared. This is going to be 2, a squared, and then 2 squared is 4. Well, now I can simplify that term yet again, because 2 over 4 is 1/2. So this is a squared minus 1/2 a squared. Well, this 1 of something minus a half of something leaves you with half of that thing. So this is 1/2, the square root of 1/2 of a squared. Um, Let me give myself a little bit more room to write this. So moving that piece over here. Well, now, what is the square root of 1/2? Well, 1 over root 2. What is, no, let me actually write stuff down. So this piece is just along for the ride. The square root of 1/2 is 1 over root 2, and the square root of a squared is just a. So multiply by root 2, then divide by root 2, cancels. So we're left with an a on top, and then times divide by 2, and then multiply by a. Well, this is just a squared over 2. So this is the maximum area. Ah, oh my gosh, all of that work. Yes, this is the maximum area of the function. Or sorry, this is the maximum area of the isosceles triangle that we drew here. Again, a very long-winded problem, but there's no like related rates piece. Like the hardest part of this is interpreting what it has and plugging that into functions that we are able to handle. And again, I'd even say the only really challenging part of this problem is the fact that we don't know what A is, and that makes us feel like once we get the area that we actually do want to take the derivative of, right? Like we took the derivative of this with respect to x, we doubted ourselves because it felt like A was another unknown, but we're pretending that we do know what A is. So I think the most challenging part of this problem is just recognizing, hey, I'm pretending to know what A is. So can I solve this here? Yeah, regardless, we just use Pythagorean theorem on the inside to do something clever that did give us a way to write the area in terms of just x and a. So very good. This is this whole back and forth with optimization problems. You draw a picture, try and think of writing the scenario into something that we can optimize, get our constraints, use those constraints to get our optimization into a single variable, and then do the whole critical numbers thing from there. Okay, so very good.